Alright, well, we've covered really our first major measure of dispersion that we can really use statistically. It's the sum of the squared deviations. You can figure out that you get the score, you subtract it from the mean, and you square things. We use x as the score. Mu, the u symbol, is used as the mean because it's coming from a population. But now, what I wanted to chat about was situation in C4. Consider the following two data sets. Consider data set number 3. The numbers are 1, 2, and 3. And consider data set number 4. Uh-oh, gonna sneeze. Maybe not. Data set number 4. You have 1, 1, 1, 2, 2, 2, and 3, 3, 3. Now, when you look at those two data sets, how do they actually look as far as measures of dispersion? Does one data set look more dispersed than the other? Most people would argue that they really look the same as far as measures of dispersion. It's 1s, 2s, and 3s in each one of them. But if I have you actually compute the sums of squares for each one, you'll actually get a slightly different value. Data set number 3, can you figure out what the sums of squares will be for that? If it's 3 consecutive numbers, the sums of the squares will always be 2. 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared. Add it all up and you get the sums of squares of 2. Data set number 4 is also very interesting. It's 1s, 2s, and 3s, so the mean is 2. But basically you're going to get, if you do the math on that, 1 minus 2 3 times. So that's going to be 1, 2, and 3. And then the 2s will give you zeros. And then the 3s will give you another 1. So if you were to actually get the sum of the square deviations for data set number 4, the sums of squares would probably be 6. So in this case, the sums of squares for data set 4 are 6. The sums of squares for data set 3 is 2. Now this doesn't seem fair because data set 4 doesn't really have more dispersion in it. Why does it come out to be so much larger? It comes out to be so much larger because there are a bunch more scores in there. There are 9 scores in that data set. So if you have an unequal sample size, sums of squares is not your best bet to get an unbiased measure of dispersion. Data set 4 just has more numbers in it, so that's why its number is greater. But there is a way to fix that. And the way to fix that is to compute the second main measure of dispersion, and it is called variance. And it's got the Greek symbol sigma squared. You don't have to square anything. The way you get variance is you take the sums of squares and you divide it by n. So if we were to take data set number 3, the numbers 1, 2, and 3, the sums of squares was what? 2. The n was 3, so we get a variance score of 2/3, 0.67. What about data set number 4? The sums of squares was 6, but how many numbers are in there? 9. 6 over 9 is also 2/3. So if you have different sample sizes, variance is a much more useful measure of dispersion than the sums of squares. And finally, last but not least, the other measure of dispersion that's useful, besides sums of squares, variance, is called the standard deviation. And the standard deviation is the square root of the variance. So it's just got the symbol sigma, so you could take the square root of 0.67. I don't remember what that number is, but do it on your calculator, and that is the standard deviation. Basically, the standard deviation is how far away from the mean is any given score. So standard deviation, variance, and sums of squares are our 3 primary measures of dispersion. Sums of squares can be biased if you have different sample sizes. Variance is a more fair indicator, and standard D is also used a lot. So hopefully this makes good sense to you. Thanks. Bye-bye.